So we mentioned the different numbers in the reservoirs in terms of the amount of carbon stored in them. It's kind of interesting to change the reservoir sizes to correspond to the differences. So here we are, atmosphere, tiny sliver holding 600 petagram carbon when this was done in 2013. Obviously now it's over 800. And then we have again the fluxes, so we are adding about 10 petagram carbon per year in terms of fossil fuel burning, resulting in 250 petagrams addition per year to the reservoir size. So that's the red part here, the anthropogenic part from the ocean and so on. So this is the net ocean uptake of 2 petagram carbon, and volcanoes add about 0.2 petagram carbon per year. You have gas exchange here, 60 petagram carbon per year out and in. There is photosynthesis and respiration, but you can just combine them into the gas exchange. That's how it would occur. From the soils, you have respiration adding 100 petagram carbon per year, so you can see the relative size of the soil reservoir at 2000 petagram carbon, much smaller than the ocean. And about 3 times larger than the atmosphere. Vegetation here at 500 petagram carbon with flux of or growth of 30 petagram carbon, and you have photosynthesis, deforestation, net land uptake, and so on at 1 petagram carbon per year, 3 petagram carbon per year, and 100 petagram carbon per year in terms of photosynthesis that is going to add to the reservoir here. Permafrost almost as big as the soil at 17 petagram carbon per year, but this is facing great problems. I keep forgetting the laser pointer. That as global warming happens and permafrost thaws, there is potential for positive feedbacks, because if the methane and CO2 get released, it could accelerate the warming and further accelerate the permafrost thawing. But it turns out that the issue is more complicated, because the thawing of the permafrost is creating some lakes on top of the soil, and the lakes are having some phytoplankton and water carbon cycle, which may be affecting the net balance here, and so on and so forth. Fossil fuels, 2000 petagram carbon per year with the change of 365 petagram carbon because of human activities. So you can see that's almost as big as the soils, but both of these estimates are kind of uncertain, especially the fossil fuels. We don't always know the reservoirs. Burial at 0.2 petagram carbon per year. So if you look at the flux here of or the growth here of 150 petagram carbon per year in the ocean with this reservoir size and this flux, you can compute the residence time. So you divide this by the flux, which gives you some millions of years of, or at least let's say 0.2, 800,000 years of residence time, and 1750 petagram in the surface sediment. Of course, there is a deeper layer as well. So it's just kind of interesting to see where most of the carbon is in terms of reservoirs, but obviously at anthropogenic time scales, it's these fluxes and the growth in the atmosphere that we worry most about. Plus, growth in the ocean is worrisome because of ocean acidification, which we will talk about later in this chapter. Respiration can increase because of the warming. Permafrost can thaw, and the question about fossil fuels is not how much there is, but if we take all of it out and burn it, how much carbon is going to be put into the system that is active and can cause global warming. So you can think that maybe we quickly make changes so that there is enough fossil fuel for us to make the transition to a safe decarbonization. Okay, so let's look at the animation that is at this site in at Berkeley, which kind of runs through the carbon cycle, the fluxes since the Industrial Revolution. Since I am capturing the screen, this should work, hopefully. Let paste and go. So this is the carbon cycle website of Berkeley Earth, which also puts out its own temperature record reconstruction that we looked at in the first chapter. So let me start this animation and then put it in the display mode. So let's play it. So we have oops, the person's name shows up here, but basically we are moving stuff from the rocks, Earth's crust at geologic time scales. Fossil fuels, did it run through the whole cycle? Fossil fuels are being burned at a certain rate, and we are exchanging with the ocean, ocean dissolved organic carbons and ocean life. You can see how it's changing. Atmosphere, how it's increasing from 1800s to whatever year, most recent year it will go to. There is the carbon exchange. Oops, I cannot do a laser pointer here because this is not PPT. So you can see per year how they increase as the clock ticks along here, and you can see the net human land use change, photosynthesis, respiration, and fire. So wildfires are also included. Living and dead biosphere, runoff that goes into the ocean, near surface dissolved CO2, deeper reservoirs here going from 37,000 from the pre-industrial level to increasing each year, fossil fuel depleting, and so on and so forth. So it's just kind of cute to look at the numbers. Such counters now exist for everything from the deficits in economy, population growth, carbon growth, and this one goes to 2017. That is the latest data they have, which reached 865 gigaton in the atmosphere. I'm not going to play it again. So I just wanted to give you a sense that this website provides a cute animation that you can go and look at. Okay, so this is just to give you an idea of the relative sizes, but it's also a place where you can see how you would compute residence times. And that is important because if the deep ocean has a very long residence time, then whatever we can sequester to the bottom of the ocean out of the system can stay there for a long time, and literally geologic time scale. So if global warming affects the photosynthesis and the carbon cycle in the ocean in a way that it reduces production and export, then the buildup in the atmosphere is going to accelerate. Whereas if the ocean continues to increase in primary production and export, then obviously you will damp the buildup in the atmosphere. Just like ocean is taking up the heat and modulating the warming and slowing down the warming in the atmosphere, carbon cycle could do the same, except we have all the evidence that suggests that warming of the ocean creates a stable stratification, which makes it harder to mix nutrients into the euphotic zone, the region of the upper ocean where there is enough light to drive photosynthesis and carbon uptake, and of course carbon export. As long as there is photosynthesis, there is some export. So what is not clear, we will see what euphotic zone is later on and the carbon cycle in the ocean later on. What is not clear is when the stratification increases because of the warming, because of global warming, whether other species like what are called nitrogen fixers, which can directly fix dinitrogen from the water and produce nutrients to do photosynthesis, will somehow compensate for the loss of other phytoplankton species that depend on nitrate or ammonium for photosynthesis. This is not very clear, but people closely watch whether nitrogen fixation is increasing anywhere. Of course, there is a question of acidification, which we will look at as well. So if increasing CO2 keeps driving acidification and destroys, let's say, corals or species like coccolithophores and other calcifying organisms, then you could have other consequences, because corals are like the rainforests of the ocean, where even though they are in warm waters where nutrients are not that abundant, they can create a recycling system which drives very healthy primary production and secondary, tertiary production, and so on. So there is a lot of recycling happening in coral and warm waters, the so-called coral triangle, for example, around the maritime continent, Australia, Great Barrier Reef, Philippines, and so on. How these will respond to ocean acidification needs to be seen. But you get a sense of how big a role ocean plays and how carbon cycle reservoir is the biggest in the ocean. Okay, so that's just a nice way to add a bit more information.